Welcome back, everybody. It's a new week, new lecture. This is the last lecture that we are going to talk about SAM, right? As we said, we have been discussing on this, but this is one of the most important results on this class, right? So discussing on this new way of smoothing our solution rather than just filtering. Quick summary of what we did last lecture, right, on the square root SAM. So we were discussing on how to make this more efficient. So remember, at the end, we convert our problem into something like this, right? This is just solving a linear system. We have linearized, of course, because the functions inside were nonlinear. But after some manipulations, we got like this result. And then the problem that we solved last lecture was, okay, how to solve this efficiently, right? Do we just apply like straightforward normal equation, or because the problem has some structure, we can actually exploit this, right? And it turns out that we can do a lot of things. Well, the first one was showing that the adjacency matrix, this square, this multiplication of the square matrix turns out to be actually the information matrix. And we know that we can factorize this, for instance, with Cholesky, right? So this is the result, and R, in this case, it's an upper triangular matrix. In this case, we don't need the other Cholesky, which transposes the second term, because we are not doing, we don't need this to be, we don't need the transpose to be the second one, but it could be perfectly this one, this other transformation, LLT, and still what we need to do next after the factorization is solve two linear system. We have here a triangular matrix, so solving this is very efficient. We just do back substitution. Remember that we start with those variables that only have one dependence, and then we substitute this solution as we, let's say, increase the number, increase the row that we are evaluating, right? The equation that we are evaluating. And the same happens for a second time, right? So we also need to do, forward substitution on this equation, right? So that was it. Did anyone try to play around with the Jupyter notebook? It's on Canvas, I'm sure. It wasn't. But it was in GitHub. Who is using GitHub, by the way? Class GitHub. No, like class GitHub. No one? Yeah, okay. And Canvas? Like more generally, okay, so you use everything. I think we have everything everywhere. Okay, so no one has tried to play around a little with this Jupyter notebook, trying to see if factorizations work well or not? No? Okay, maybe you want to try that at some point. I think it's easy to see what things mean if you have like an example. Okay, wait, so you haven't tried it because you are studying for the exam? Yes, okay. Regarding the exam, in case that you didn't know, there was an announcement this Saturday or Sunday. We provided the last year exam, in case that you wanted to see like a sample of what this exam is going to be. Well, for those of you that haven't checked Canvas, it's there. The exam, it's not supposed to be like, it's going to be similar to this one, not the same, but similar. So there's like a couple of everything. Some problems to solve, some theoretical questions, and well, basically things practical. You can do everything without need of any, just with your some pen, and there's no need to have calculations here, right? So, yes. Yes. That's the other thing that is written in Canvas. You can use like a piece of sheet, just written by you or with handwritten, and there you can put whatever you want. Okay. So what else did we discuss last day? There's another method. In this case, Cholesky requires the matrix to be positive definite. QR is not doing, does not require like so many well, does not require like this to be even square, right? So here we can have any matrix of any size, and in this case, the adjacency matrix, we know that usually it's going to be rectangular, right? So we know that we've multiplied this matrix or any matrix by this also normal matrix. It's kind of, we are rotating this matrix into this higher dimensional space. At the end, we are going to get like an upper triangular matrix as well. Right, so there's going to be a bunch of zeros, and this is actually what we want, right? Because then, after doing this factorization, we just need to solve this new problem, right? So in this case, it's just one backward substitution, and then this d vector, we know that was after transforming also b, right? So in terms of efficiency, well, they are kind of on par, like Cholesky and QR. So it's not that one is better than the other. Might depend on the problem, but one has advantages. I mean, there's not a clear winner, right? Okay, and then we talk about the Schur complement. If you remember, what we use is that if we have an information matrix, the block corresponding to landmarks, in case that we had landmarks, is diagonal, right? As we were defining things, we never observe, there's never an observation between two landmarks. There was always an observation between a state and a landmark, right? At the end, everything gets connected, but not directly. So this is interesting because then a diagonal matrix is easy to invert. And basically, well, this is what we were doing. So we know that this submatrix is easy to invert. Then we use the Schur complement to calculate this block of information, right, after removing this part. And that was it. Then we just solved the system. We are going to discuss today like another point of view of what we did last day, just directly applying the Schur complement, right? We'll see that in fact this is equivalent to marginalizing all landmarks, right? And then we have this new equivalent information matrix that is expressing the same problem, but we have simply removed some variables. Okay, and then we talk about node ordering, right, in the graph. So this is another thing that we can still do. Since this matrix, this adjacency matrix is sparse, so is the information matrix here, built this way. It's not just that we can apply directly like Cholesky and this is going to be fine. We can do better if these factorizations come already like with some order, right? And then we discuss what is the effect of starting with nodes that are fully connected. We are basically going to add like many more edges. So that means that here the linear algebra is going to have more terms. But if we start the other way around with nodes that are less connected, then there's going to be like less extra edges that are generated after eliminating each of the nodes. So, well, this is just for you to know, but I think if you play around with the Jupyter notebook, you will see that the difference is considerable. Now, if you put this on large-scale problems, this is really crucial, right? And in this case, I was on this Jupyter notebook. There's just straightforward ordering based on number of nodes, but there's actually other heuristics that you can use, right? Some of them are publications, like, so we have column permutations, column, etc. Okay, so again, see the Jupyter notebook. I think, yes, last class is basically summarized not by these things, but actually you go there, you execute things, and you see how they perform. And I think this is the best way of seeing, well, what it means to solve these systems efficiently. Okay, so I hope by now everyone is convinced that we can solve these kind of problems very efficiently. It depends on the structure of the problem, but still, if we don't have like a very dense graph, we can do very well. Not linear, but still we can do very well. It's not as bad as just doing the inversion of the matrix. That, remember, the complexity of this is n cube. But with this extra exploitation of the problem structure, we can do much better. Okay, next topic is, again, efficiency is really something that we are always discussing about, right? So there's still another thing that we can do to make this even more efficient. It's not that we're obsessed, it's that this is really, this is a real problem, right? If you want to get things like real time, or you have large data sets, efficiency here on how you calculate things is important. So then this is the work of Gaius in 2008. Basically, it's incremental SAM. And the intuition is, okay, so we have calculated this adjacency matrix or the information matrix, whatever you want, right? We have a new observation. This new observation might be just an odometry factor. The question is, do we need to recalculate things again? Right? So it depends on the information that we are adding to the system. It might not be necessary. In fact, there's going to be a way very efficient just to consider these new observations and still use the previous adjacency matrix or the previous information matrix. Okay, so let me summarize this. New observations. What we are going to do is we are going to update the adjacency matrix, also the already factorized matrix. Without re-evaluation. Okay, so why not? Sounds like a good idea, right? You have already a very large matrix. You don't really want to re-evaluate things again because maybe your solution hasn't changed much, right? The best estimation is still going to be very close. But you want to consider this new observation, whatever it is, right? So there's a way for doing this, and I'm going to explain it just now. It's basically it's based on the QR factorization because, well, we'll see that there's like some properties of this factorization that makes this a little more convenient for incremental updates. Okay, so this is what we defined last day. We can also rewrite things like this. Remember that orthonormal matrix, the inverse is just transposing. So that's very convenient. And now what we have is a new observation, right? And when we have a new observation, well, basically, one of the things that we need to do is where to put this observation, right? So in this case, we are going to assume that this new observation is going to be like at the bottom, right? So it's the last element on the vector, if you prefer. And then the new QR factorization, it's going to be very similar to the previous one. Here we are going to have like the previous orthonormal matrix, and the new normal and the new vector that we are adding is this, right? So we have a bunch of zeros, and basically we are adding one dimension, right? And if we do that, what can be a vector that is already normal to all the, yes, orthonormal to all the vectors that are inside. So this one, right? A lot of zeros here and just a one at the end. Okay, so we are just increasing this matrix a little bit. And then let me write the adjacency matrix. This is the previous one. And what we are adding here, this is the new observation, right? Remember that this observation could be on this matrix could be like we are observing landmark and from a position, right? So in this case, we were defining this as J, and here H, or the other way around, or if we have, or if we had an odometry, we had something like this, right? Basically, what I'm writing here is this column. This is the new observation that we are adding. So new one comes, and then we add a new, and this is what I'm calling W. Okay. So nothing, I mean, this step is clear. It sounds trivial, but we'll see that actually there's a lot of advantages of doing things this way. And then what this thing, yeah, by the way, here, I'm just multiplying, right? I'm just doing this. So this should be equal to R. And then if we have R, whatever it is, it should be like our previous R, and then this new element that we are adding here. Right? So the same happens for the D vector, right? We have the D vector, and then we are going to add whatever new value we have. Okay, so let me write just a little more clearly what are these vectors here. Right, so in this case, this is for the odometry, and this is for the observation, right, as I said. Right, and in between we have zeros, right? So these are sparse vectors. And then basically the idea is that we are going to have, we want to calculate this new this new upper triangular matrix, that what it is our previous calculated R matrix. This is upper triangular, and then what we have added here is this new column, right? In this case, not all of it is going to be like dense, but maybe there's like elements here, right? So this is how this new R matrix is if we do this thing incrementally this way, right? We are not refactorizing R, we are just adding a new column, and then we'll see how we need to rotate this in order to get a new upper triangular matrix. Right, so for this, what we are going to be using is what is called the Givens rotation. I'm going to give an intuition of what it is, right? But the idea is that, so you know, let me write here. Objective, make R again. So we have this matrix that is almost close to be upper triangular, but we have like here some elements just on the last row that are not allowing for this. So in this case, instead of, we could be calculating directly QR here, right? And then we'll have a full matrix of an orthonormal matrix transforming all elements. Or in this case, what we can do is some incremental with respect to the previous one that allows these elements here just to be 0 again, right? So we are going to propose like new rotations. And a way for doing this is given rotations. Yes? We expand the Q matrix. These are going to be 0 because this is the only way that we can make this orthonormal. Yes, we added zeros to all the previous dimensions and 1 into the new dimension. Okay, good point. But still, we don't have an upper triangular matrix, and this is what we are going to try to solve now. Okay, so here we have this, given rotations. The idea is simple. Basically, what we have is a matrix like this, right? It's kind of resembles a two-dimensional rotation. And what we do is we multiply any matrix that we have such that then this resultant matrix is going to be like this. Right? So if you see now this is upper triangular, this is for the two-dimensional case, but what we are doing here basically it's eliminating this, and for doing that we need to multiply all the other elements. Right? So there's a combination of sinus and cosinus, right, that will make this element 0, right? Basically, you just need to multiply this by this ABC, and well, there's an equation that will satisfy this, and once you find this, then, well, the other values need to be updated accordingly, because if not, this will not be equal. So this is for the two-dimensional case. Who has, I think you have done this before, right, in class? Okay, so for those who haven't seen this, the idea starts with 2D, and then we are going to apply also this to the whole matrix, right? So instead of having now just this 2 by 2 matrix, we are going to have a large matrix. Okay. So by the way, this is one of the ways of solving QR, right? But you simply do this with the full matrix. One way of solving it is with given rotation. Well, there's others, which you have already studied. But here we are just using this to calculate this very last row that is very annoying, but which makes the matrix not upper triangular. Okay, so in this case, if we had like a larger matrix, this thing will look like this, right? We have whatever elements before. Remember that what we have is an upper triangular matrix, kind of, and then we have elements on the last row, more or less, right? And all the other terms are 0. Well, yeah. So what is this matrix doing? We have a diagonal that is once, it's almost the identity, except for these elements, this cosinus and sinus, same as we had before. So in this case, this is going to be our new phi matrix. And then what we are going to do is multiply this to this upper triangular matrix that we had before well, yeah. Where we know that we have this element here. This element corresponds to this one, right? So that's why we have chosen this column and not, I don't know, something here, right? So then as a result, after applying this, well, basically we have the identity, almost the identity, so we should have something very similar. But as a result, what we are going to have is that here this element now is 0. Right? And here there's going to be a bunch of new elements that maybe before they were 0, but now they are going to be different, right? Because we have just rotated them. And then, well, this new upper triangular matrix, it's not exactly the same, right? There's going to be still like all these elements here that are just also being modified. So you see that this comes at a cost. You cannot really do this everywhere. But if this number of non-zero elements that we are adding in this row is small enough, we can still do this very efficiently. So we go on certain order. We basically eliminate all these zeros that are below the diagonal. And at the end, we are going to get more non-zeros than before, but there's no need for us to factorize the matrix again. So this is great. Then what happens with the new matrix of this orthonormal matrix, this matrix of, let's say, rotations for A, is that we have multiplied this by this matrix. Right, and then basically what we have is a new orthonormal matrix. The given rotations is not adding anything. There's still the orthonormality on Q is preserved, right? Because we just have cosinus and sinus. Okay, so this is how we update this, and then we do this until we get, like, again, upper triangular matrix. Okay, so basically this is the ISAM algorithm. It was taken from linear algebra, but the idea is that you can do this incrementally if the observation is not really changing a lot of variables. If here we'll have like a lot of non-zero elements, or here we have like many more other things, maybe this is not the best way to go. Right? So let me write now this algorithm, the ISAM. So first, new observation or new factor if you want, right? So what we do is we update R. Then the second, we do Given's rotation. Until this R is again upper triangular. And then we just solve this again. Right? So depends on the nature of this problem. This can be easy. It could be just like several given rotations, or it can be like thousands, right? So we don't really want like to do a lot of them. Maybe it's better just to refactorize again. But if it's few of them, this is still very efficient. What's the problem? Is that we do this one time, okay? We do this for a second time, right? So if we do this for a second time, then maybe instead of just updating this thing, we are also updating this. There's going to be like more non-zeros that are appearing, right? So you see that comments. So eventually sparsity is lost. Okay, but this is not really a bad thing, because for the time being, maybe we have saved a lot of computational time, so this is good. It basically means that at some point, we need to relinearize, we need to recalculate the upper triangular matrix again, right? So, and this is one of the kind of hard parts, right? When we decide to recalculate things or when we just do an incremental update. Still, these incremental updates are very, very efficient. So this really is like a thing. Okay. And this also brings us to the, well, again, this discussion on the ordering. So what we were doing is all the time add this factor at the very end. But maybe for the optimal way of, given the structure or the topology of the graph, it's not the best place to put this new node. Maybe it was like not connected and we want to put it somewhere. But because this incremental, how this incremental algorithm works, we need always this to be like on a place that it's gonna be like less number of rotations. Imagine that you start with your new, instead of putting this here, you put it like at the very top, right? So this is your new. So that means that you are gonna be like doing a lot of things. You need to eliminate all these zeros, right? So it's simply more convenient to place always here the new vector. Okay, so still, well, this is an alternative. It's not always used. Sometimes you just want to recalculate things, but if you had like an application where actually you really need to have like fresh data continuously, and maybe you don't need to recalculate things because they don't change that much, this ISAM algorithm is very, very convenient. Okay. Any question on the ISAM? I'm not going to ask, it's not on the problem set, but still. One question, who has started doing something with problem set 3? Opening? You have opened? You have solved it? Okay, but open the PDF or you have played with the node? Oh, okay. Well, it's going to look familiar. So I think problem set 2 was a little more new in this sense. You needed time to adjust, but problem set 3 is going to be a little more familiar because the environment is very similar. Okay, let's change a little the topic. So we have discussed ISAM. Let's talk about something that we started discussing on lecture 9, if I remember correctly. It was data association, but in that case we were discussing data association for filtering. Right now that we have this smoothing paradigm where things are just being reevaluated, we don't need to, once we add information to the filter, it's not going to be there forever, so we can undo things. Then data association, it's going to be also a little more relaxed, right? Remember that before we had to do the assumption of whatever we had decided, that must be true, right? And that was like really, really limiting, or at least it was very constraining. Now, well, we always have the full trajectory, so we'll see that we can do still some things, and data association is not going to be like so affected for that. Okay, so just as an example, imagine as always we have like some trajectory. And here we have two landmarks. Very, very close by. Right? And here we have two landmarks again. right? And what we are saying is maybe we have observed this landmark from this position. Maybe we have observed this landmark from this other position, and the same happens here, right? So that's why we have created, we have always decided to do a new landmark because whatever decision in our algorithm was doing, but there's no way to undo it, right? So now what we have is 4 landmarks when, well, maybe these things are exactly the same landmark, and this thing is the same landmark, right? So what's the, how does this look like in our adjacency matrix? So I'm going to sketch like this very easily. So remember, we have here like some odometry, something like this. And then what we were seeing is that here we have landmarks, and here we have positions, right? So in this case, first landmark, we are observing from position 1, position 0. Here, position 1, we are observing landmark 2. From position 1, we are also observing landmark 3, and from position 2, we are observing landmark 4, right? So we have this kind of, I'm just sketching the adjacency. This is something useful for you to know when you implement this in problem set 3. It's going to be useful to know exactly what is in each row, what are the indexes, on this kind of thing. But does anybody disagree with this graph? Is this the same graph that you would draw if you were? Okay, maybe you want to try to draw what is the next, because now we are going to do the following thing. Now imagine that we have decided that these 2 landmarks are the same. So here, instead of having 4 landmarks, we are going to have only 2 landmarks, right? And still here we have like some mix. So, yes. This. So this corresponds to the observation, the Jacobian of the observation, like this, right? So in this case, this Jacobian is with respect to the landmark. We are calculating our observation function, and here this Jacobian is just a derivative with respect to the landmark, and here this Jacobian is with respect to the state. So that means that we always, when we observe a landmark, there's always 2 Jacobians, right? The others are independent. It doesn't matter what are the other variables. So that means that each point of this represents one of these Jacobians. This is diagonal just because we are observing landmark 1 time. We are observing then landmark 2, landmark 3, and landmark 4. So it's simply a sequence, but it has not to be diagonal. What is diagonal is this, right? So you have this, and then this block, this is diagonal by construction. But this, on the adjacency matrix, it might not be the diagonal. You might be observing landmarks multiple times. Yes? You are asking about what is the content of each of these subblocks? No. Okay, so this is just the Jacobian. It's going to be different numbers, usually, right? Although it's a strange case. But usually, yes, they are just different values. Here, we are not really worried about the value, the numerical value. Actually, remember that these are actually block matrices. What we are interested is in knowing which of these blocks are 0 and which of these blocks are going to be non-zero a priori, right? Because we have Jacobians. And this is what I'm indicating here. So when I'm going to ask you to sketch like an adjacency matrix, I'm not asking you to write here like J of 1, J of 2, right? This sketch is like a little more superficial. I'm just asking you which block elements in this matrix are non-zero. right? So that means, for instance, if we go here to this graph, let's take a look at this, right? So this row corresponds to this observation. So what is happening is that from x0, here, x0, hold on. Right, from x0, we are observing landmark 1. This is what I'm saying. So then you come here to the adjacency matrix, and what you see is that all elements are 0 except for this, x, here, and this landmark are at 1. Okay? It's going to be, this Jacobian is going to be 0 for second landmark because we are not observing the second landmark. So the Jacobian there, the derivative is going to be 0. Right? So that's what I'm doing here, like maybe going a little straightforward, but the idea is that this is how we built the adjacency matrix 2 lectures ago, and now I'm just simplifying this a lot, extremely, and I'm forgetting about the Jacobians, and I'm just saying, look, from all these, in this matrix, all the block elements that are not going to be 0 are going to be dots. Okay, is this clear? I think this is a very good question because now, in case that someone else was in the same point, you have, and maybe on the exam you have like a similar question to this. Yes? So the question is, why do we have two dots on each of these rows on the adjacency matrix? You need two dots because it's not that you're observing the landmark by itself. What you are, remember that these are factor graphs, and factors are always observations. And in this case, factors are modulating the nodes corresponding to variables. Landmarks, in this case, it's a node corresponding to variable. This is the unknown. This is our variable that we want to calculate. And the same is for x0, right, the trajectory. So this variable node corresponds to the initial position of our trajectory. What we see here is some observation, right, in this case, C1. And this is what the factor is just giving you, like, it's modulating the distribution between these two variables, right? So that means that when you add, like, information into your adjacency matrix, it's only going to be related to the landmark and the x, right? So this is what you are saying here. It's not that you add information about one of the things by itself. It's that this is the relation between the two of them, right? So remember this. Then when you equal this adjacency matrix, it's always to some b. Remember that b was like some sort of residual after accumulating things. And what we want to know is how close we are to the observations, to matching them, right? So here, I think it was h evaluated minus z, or the other way around, right? So that's what we are relating. So the two things, right? But it doesn't mean that we're evaluating one and not the other. No, the two of them must be considered here. Okay, so if you redo the Jacobians from 2 lectures ago, you will see that this is the only possible signal that is not 0. All the others, according to this observation, should be 0, because you are not, I mean, this is the position where you are taking the observation, and this is the landmark you are seeing. You are not seeing any other landmark, not from this position, and this observation is just taken from here. Okay, now what I ask you to do is spend 1 minute and write the new graph. And now this time, let's write the new graph knowing that, let's say 1 equals to the previous one, and 2 equals, so what we are doing is grouping them, right, like this. So sketch the new graph. Okay, start with pen or with laptop or whatever, or sketch it in your mind. Remember, the only thing that we have done is grouping two of these landmarks, or saying now we don't have like so many nodes. What we have is, well, that we have merged them. Fused. Okay, let's start with the simple part. The simple part is the odometry. So we are going to have something like this. This hasn't changed, right? Who has changed it? You have a question? You have a question. Why is, oh yeah, this is my bad. It's 2, it should be 2, right? Because we only have 1, 2, 0, 1, and 2. Okay, so this is kind of the blocked, this is kind of the diagonal, almost diagonal, block diagonal thing that we were talking about when we always comment on odometry. So this hasn't changed. Now what has changed is the observations for landmarks. So what should I write here? Is this point the same? Yes. Okay. And what about this one? What I'm observing now, remember, is that now this is M1 prime, if you want. So what I'm observing now is 1. Okay, let's go for the second one. Let's call this Z2, right? So for Z2, where are we observing this? Here. What? X1, yes. Okay, and where is the other, basically which landmark we are observing that we should be changing here? Do we do the diagonal thing? Here? Here, right, right. So again, we are just, this is the same thing. The only thing we are doing is here, instead of these two being like two different landmarks, we have grouped them into the same one, right? So in this case, by sketching the graph, it's very easy to undo any wrong data association. Before we were saying, oh, once you add like new information, there's no way for you to go away. It's not true, because now what you have is, okay, you need to relinearize things, but still you don't have like any prior information from wrong associations from before. So you can undo this very easily. What about the third one, right? So this is 3. 3 comes from 1. This is not changed here. And then what we are seeing is landmark 2, right? And the same goes for this, right? So here we are in X2, and what we are seeing is this. Okay. Yes. No, well, this is not really diagonal, so I was just writing it this way, but actually it should be something like this. No, this part doesn't change. We haven't changed anything here on the graph structure, so we have the same observations. I'm writing it this way because diagonal would be just a line, but in this case I was writing this like, yeah, it's kind of a diagonal with some elements, right? So, yeah, if you write all points, it's going to look like this, right? So, okay, is it now a little more clear how you can build like an adjacency matrix? Yes, we can do another example if you want. Let's. This. This is a very good question. So how is related odometry with landmarks? Remember that odometry was the result of doing this function, right? So this is the factor that we are considering here. We need to match the current position with the previous position after executing some action. So there's no landmark here, right? This is independent of landmarks. So that's why you don't have here any element that is non-zero. All of them are going to be zero because this is independent. Yes. Yes. But the great thing about the adjacency matrix is that at this point, we are not aggregating information. This is not the information matrix. When you do this, then of course, you are considering like all things at the same time, right? But when we are just writing the adjacency matrix, what we write here is variables, and here, observations, right? So this is a very clean way to express the problem that we have, right? So here we are just writing variables, and here observations. And for odometry, we are not assuming anything about landmarks. We are just executing actions. Later, yes, of course, these variables are going to be affected. But the whole point of smoothing and mapping is that you never condition with whatever other thing into your information matrix, even in your adjacency matrix. You always maintain things clean. If you make that, then things are sparse. If you start adding information here, like saying, okay, so now, well, in information form, by the way, conditioning is adding information. If you start saying, yeah, there should be here this other factor or this other thing, if you start adding things, whatever it is, this result, then sparsity is going to be broken, right? So this is what happened with EKF. We were all the time adding information, doing updates, doing this incrementally, propagate, correct, propagate all the time. So eventually, our covariance matrix became like dense. The same happened for the information, right? Here, this is the important thing about SAM. That's why it's, I think, works so well. You always preserve sparsity by never adding information to your solution. You just calculate your best estimate. But the graph of the structure, the graph structure is always the same. You cannot start adding information because you have solved the problem, and of course there's going to be relations between, there's going to be cross terms here, right? If you do if you do this, of course there's going to be elements here, right? We have discussed, maybe they are not very large, but still there's going to be something. This is a dense matrix. But, so this is dense, but this is sparse. And this is where we want to be, always in sparsity, right? If you want to work with dense matrices, that means that your state variables are not large. So that's fine. Then the best thing you can do probably is EKF with stack variables, right? So you just put there on a large vector, whatever it is, and then you solve things. You invert your covariances, and that's it, right? This is the best thing you can do, considering everything. But if you want to do this in an efficient way, sparsity must be preserved, and this is the only way, right? So we never change this structure on the adjacency. This should be a point that everyone should have like very, very, very clear, super clear, right? Otherwise, there's no point on explaining smoothing this way, right? You just do things by brute force, invert your matrix, and then you have a solution. But this is a way on how to calculate or estimate variables when your dimensionality grows a lot. Everyone is clear with this? Yes? Okay, now let's do an example. Why not? Okay, so for instance, I don't know. It can be something like this. Do you want me to add more? Okay, and then let's add like some landmarks. Okay, so who wants to observe this? This guy, for instance, right? I'm going to grade it, actually, this color a little differently. Who wants to see this? This guy, for instance. This guy. Now we have a second landmark. Okay, so what else? I mean, this is your example. What else do you want to do? Do you want to observe? Do you want more landmarks? 3 landmarks. Something like this, okay? Why not? More? Okay, I'm going to advance like a little thing. This is for when we explain, okay, no, wait. let's do an example. Okay, later can be more complicated, but it's another important thing that you need to take from this class, right? So what is the best way to describe a problem? Always with a graphical, well, in this case, we use graphical models, right? But they are very expressive, and with this, you can have an idea of what's going on. So in this case, this is the trajectory of the robot, and what we are saying is, look, we have all these positions of our robot over time, and then this is how we are seeing landmarks, right? So at the end, all this can be represented by a graph. Imagine that you start putting observations, Z1, Z2. This is not really useful, right? And this is not expressive. But this, on the other hand, you see like connections, you see things graphically, right? I think it's useful. Okay, so do you want to start doing the adjacency of this? Again, just sketch like those elements that are going to be non-zero, right, a priori, and all 0 elements, don't write anything. Yeah, I'm going to write this. Right, so here this is going to be for x0, x1, x2, x3, x4. This is going to help, right? So we know that in each column corresponds to an unknown variable that we want to calculate. It's simply the way that we have described the adjacency matrix. And then maybe you start with here. So I'm going to write ODOM 1, ODOM 2, ODOM 3. How many do we have? Okay. And then okay. So how is this sketch going? We have 7, yes. Okay, so what about this? We start with odometry. We start with odometry? Okay. So this is the first factor that we have, right? We need to include all factors. Remember, here I'm writing them as dots. And nodes representing variables as triangles or circles. We should be using here circles as well, but since we have orientation, that's why I'm using this little triangle. Okay, so we come here, and this was an example of an anchor factor, right? This factor, in this case, it's just modulating the probability of one of our known variables, right? So what is this? This is a prior, right? How many other nodes this is affecting? Only this, right? Okay, so this was easy. Let's go for the second factor here. Right, in this case it's x0, right? We propagate x0, and then we get as a result x1. Right, so here, yeah, and here. Remember that now we have two variables in both, so you always need to take a look exactly what these factors are connecting, right? In this case, there's just one node here. That means that, hey, there's just one non-zero element here on this adjacency matrix, right? So this is perfectly fine. Now what we have is two elements. This is connecting two elements, so we must have like two elements, right? Because the Jacobians here are going to be non-zero, at least, well, a priori, and then the other variables do not matter, because here we don't know about what's going to happen next. We are not adding information like after accumulating it. So it's just these two things. Okay, what about the next one? So odometry always looks like this. And finally, this. Okay, so we got this part. Everyone got this part. Yes? Yes? In your sketch or your mental sketch, you have something like this for odometry. Okay, now let's go for observations. We are going to start with the first observation, right? So in this case, it's relating x0 and the first landmark, right? So we know that the Jacobian of this observation, it's going to be 0 everywhere, except which parts? This one? You stop me. Left or right? Stop. Okay, I think this is a little complicated. Okay, I'm just going to write the solution, and then if you do agree, fine. If not, you raise your hand and say, okay, what's going on? Okay, so x0 and m1. Right, m1. Okay, right. So why these things are 0? Because if you do the derivative, this is of the first observation of, if you do the derivative, I don't know, with respect to m2, this is going to be 0, right? So there's no m2 here. You're not observing m2. How can you say anything with this observation about the other landmark? We know that eventually these things are going to be correlated. But just with this observation, assuming that these variables are just numbers to estimate and not distributions, this is the only thing we can say. The derivative here is 0, so that's why you add here as 0. Let's go for the second observation, right? Or landmark observation. Here we have x1 and m1, right? So again, we are here x1 and m1, okay? Let's go for the next one. So we have 3, number 3. In this case, it's connecting x2 here and first landmark. So x2. Whoa. And which landmark did we set? This one? This one. One question: does the order matter? Does the order matter here in this adjacency matrix? Okay, I think you are kind of answering, but what I mean is that if you change the order in the adjacency matrix, is this going to give you like a different information matrix? We change the order of observations. Here, we permute all the rows in whatever order. So instead of saying that now I'm observing this observation here, right after this one, it's the other way around, right? So we were following this kind of sequence, but you see, when I was writing this, maybe instead of 3, we start with 4, right? Is this going to change the information that we get? It's from different, yeah, so 3 and 4 are different. But what I ask is if the information matrix, the resultant information matrix that you get is going to be different or not. Yes. So if there's a different order in how you are putting things, is this going to affect the solution? Okay, who says yes, it's going to be different? Who says no, it's not going to be different? Okay, yes, so you are right, it's not going to be different. And why is the reason for that? The reason is that you can have your matrix, you can wait. Yeah. You can permute it, right? And in this case, we are applying just permutation with the number of rows, right? So imagine this is a permutation matrix, all zeros except some ones there that are just changing the, what we are changing is, imagine you are shuffling the number of, well, the rows. So this is what this matrix is doing, right? So we have this, and then we have this, right? And then if you apply this, what you have is this permutation matrix, and this, what is this for permutation matrix? This is the identity, right? So then the order is preserved. You are exactly whatever you had before. It's not true if you were doing permutations on the other side, right? On the other side means for variables. For variables, yes, it's going to be a different thing, right? So if you do permutations here, you are going to change your variables a little differently, and then the information is going to be different. We know that if, no, well, you don't know. You will find out soon, but if you were playing around with the Jupyter notebook from last lecture when we were permuting things, you will see that permutations actually change the information matrix, right? But it's because what we were shuffling is this number of variables. If we change the observations, that's meaningless, right? And the proof for that is that. So you have here like these permutations that at the end are going to be, I mean, it doesn't matter because then these square form are just going to compensate for all these permutations, right? No. So this matrix is just permuting the column, the rows, right? So you have a matrix, a rectangular matrix is just permuting the rows. If you want to permute the columns, this, and if you want to permute columns and columns and rows, then what you need is this, right? Basically, you need to apply permutation like on both sides, right? Because one is just shuffling, right? So, well, you can try this at home if you want. There's like, I think there's matrix permutations in this Jupyter notebook. But, at the end, what this means is that we don't really care about the order. It's simply we are following this one, but when you are building the adjacency matrix, the observations can be in whatever order. It's not true. It's not the same for the order in the variables, right? So if you change the columns, we know that this gives like much better, much more efficient solvers for the solution, right? But if you just change the observations, I mean, this is common sense, right? You just change the order of observations. We are never adding things. It doesn't matter if you solve one observation before the other. So it should be the same, right? So basically, common sense matches with this, right? Yes? Okay, yeah, one question? No. So your question is, how can we prove that we should be changing? Okay, yeah. So why order doesn't matter when we are ordering observations? I think I'm going to give you like an intuition. We are processing full trajectories. That means that we are gathering all information, right? And then we are processing everything together at the same time, right? So in this case, common sense says that if you are just accumulating everything, and there's nothing incremental, there's no filtering, there's nothing that requires your previous state, you just put there all together, this is a joint optimization, then the order of the observations doesn't matter. It matters the order of your trajectory, right? Or the order of your variables. We have discussed last lecture that actually this gives like more efficient ways for solving. So depending on the order, you're going to have more zeros or more non-zeros. But in the sense of what is the optimum order for processing the observations, it's going to be the same, right? Because we have this, well, basically these permutations at the end just cancel out. Okay, so let's finish this. What else is left? So we were talking about 3. Now we need to talk about 4. So it's here. And what is for observing? Landmark 2, right? I don't know. Yes, landmark 2. Now we have 5, which is x3 and landmark 2. So we come here. Okay, this is 3, kind of, and okay, finally, we have 6, which is x4 and m3. So here and m3. And what about the last one? x4? X0, yes. And which landmark? Third one, right? Okay. So that's it. You can make up like your own examples if you want, but at the end, you will see this much more clear when you do problem set 3. So you are asked to build like one adjacency matrix, and then you are going to solve the problem. Of course, there's going to be like, you will need to calculate Jacobians, but conceptually what is important is the order, right? So what is in what place, why your matrix should be like having these elements and these kind of things. Right, so you start with that, with this structure, and then if it's blocks or elements, well, I think that's secondary. Okay, let's do a short break, and then we'll get back, yeah, to the data association that we were discussing. Okay, it's time to get back. So we were in the middle of some discussion before explaining these sketches on on graphs, and it was the following thing, right? So data association. Basically, the question that we raise is, we can undo things, that's great, right? And what is the cost for doing this? We just need to rebuild A, the adjacency matrix, but we were going to do this anyway, right? So this allows to have like more flexibility, and nothing is permanent. I mean, if we have done a growing data association, we can undo things very easily. So this simply means that we can also think about data association in a different way, right? And there's many things here to be done, right? So we could be doing like hypothesis testing, even after a long time that we have observed something, or let's say that we can try several changes without really breaking the integrity of our estimation, right? On the other side, remember that EKF, what it needed is because it's filtering, right? Because it's filtering, it requires always to have like correct correspondences. Even if they were not correct, we must assume that they were correct, because if not, the distributions that we obtained were not tractable, right? So this was one of the prices that we paid, and now we simply have this new door open for, let's say, a new and more flexible way of doing data association, right? So this is still an open topic for discussion. Let me also do like some thoughts on what is other things that we need. So imagine that, for example, right? We are going to test like what is the distance, the Mahalanobis distance between our landmark and our observations to decide if we have a new landmark or not. This was the common thing that we did, if you remember. But now my question is, where is our covariance matrix? Right? What we have is this. This is what we have discussed so far, always information form. It has many advantages. Main one being that adding information is almost a non-expensive operation. But obtaining the covariance is not one of these advantages, right? So we know that we have here like this, right? So this is the relation. So again, we have a great opportunity of combining landmarks as we want, but then we need to obtain the covariance somehow, right? So what I'm going to explain now, or I'm going to try to motivate also, it's not just for data association, but a way for obtaining this covariance, right? The most straightforward one is to just invert. But we know that the problem has a structure, right? So if for calculating a solution, there was a better way for inverting this matrix that is going to be sparse, there's going to be also another more efficient way, right? So once we have a covariance matrix of our problem, then we can do Mahalanobis distance, or we can be doing anything, or plotting isocontours, right? Things that are useful, that we know that are useful, but you cannot really go to the, I mean, you know this, right? You cannot really go to the block of your information matrix and say, yeah, this is my information block. I just take this and I invert. This is not allowed. This was only allowed for covariances. For covariances, we know that we can take a look at blocks, and this is equivalent to marginalizing. But the inverse of these subblocks on the information is not the covariance subblock, right? So we cannot really do this. Okay, so still, don't worry, because we can do a lot of good things, and still calculating the covariance is not going to be that a problem. It's not going to be like that intense. There's also other variants, so maybe I'm not going to explain them here, but maybe you don't want to calculate the full covariance, but you just want to calculate a block. Let's say your last position or whatever landmark you're interested. So there's still things that you can do, right? There's no need to calculate everything. What I'm explaining here is how to calculate the full covariance matrix, right? So we have this. We know that covariance is the inverse of the information matrix, and this is what we have so far. And the idea is use R and RT, right? Because they are sparse. So we know how this thing factorizes. We simply need to use like these matrices, which are already giving us like a lot of help. We've seen what happens for linear equations. So back substitution is easy, right? You just go there and start calculating one-dimensional equations. I mean, equations of one variable, and you just do this iteratively. So that's great. But is there like a way to also use these nice properties of R with this inversion of matrix? So let's get to it. Definition so far written many times. Now what I'm going to add is this new term, right? So we know that this is going to be equal to the inverse of the covariance. So what we can do is multiply in both sides by the covariance. So in this case, we are going to have RTR multiplied by the covariance. And in this case here, we have, right? And this is the identity. Okay? So here, you multiply right-hand side of each of these elements on the equation by the covariance. Right? I'm just adding things. This could be a one-dimensional variable. Nothing fancy. It could be a 10,000 by 10,000 matrix. But still, this is true. Okay, so once we have this, right, then what we can do is the following. So if before what we were solving is a system of linear equations, now what we have here is instead of a vector, we have a matrix, but still we can solve this in two steps. The first one is we are going to assume that this R multiplied by covariance is a matrix, matrix I. And then this matrix I should be equal to this. So what does this mean? It means that here we solve n times the linear system, right, with back propagation. So we solve n times, no, back substitution. So you see, actually, this I, it's going to be like a vector, right? And the identity, we know that you can also take a vector. So it's basically solving n times by back substitution this equation, right? So that's what I'm writing it on a matricial form. But in fact, what we are doing is just solving vector. Right, so we have then all vectors in this Y matrix, and then we do the same for the second equation. Okay, so this is better than just going to your linear algebra library and say, let's invert this thing, right? So that's expensive, but this, and especially if there's not many non-zero elements. Here, there's small number of non-zero elements on your upper triangular matrix. This is going to be very efficient, right? So all this back substitution, very optimistically, will be almost linear. Okay, they are not, but it's close. In the worst case, we know that this is going to be dense, right, and bad. But the problem, as we have defined, assumes that there's sparsity. Right, so this for sure is not going to be like a fully dense upper triangular matrix. It's going to be many less elements, and that means that solving this is going to be efficient. Yeah. Yes. 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 So what we had before is this. Right? Vector, matrix. And then what we did is we first calculated this solution, right? And then we calculated the second linear system, right? Here what we have is the same but with matrices, right? And then we are basically taking each of the vectors in these matrices to solve. Okay, so the same procedure, but this basically allows us to calculate covariances. This is good. You can use it, by the way, in problem set 3 if you want. Or, no, it's not necessary, but if you want, you can play around with this, because you're going to be asked to calculate covariances. Or you could just be doing an inverse, direct inverse, and that's it. Okay, let's discuss another interesting topic, which is also related, as I said before, with the Schur complement, which is called landmark elimination. Okay, so now we have the following factor graph. Here, this is another example for you maybe to practice on sketching these things. I'm just going to do a small part of it. Right, so then if you sketch this, it's going to look like this. Here we have odometries, and then here we have some observations, in this case, landmark 1, and landmark 2. Right? So the idea now is the following. What we are going to do is we are going to eliminate this landmark. Because whatever reason, maybe we want to have a smaller graph or whatever, right? But if we eliminate this node, we know that what this means from the graph perspective, right? So basically we need to add like other factors just to make this problem equivalent. So the same graph with this landmark and without this landmark should be the same. So what we are saying here is that this landmark is just going to go away. So that means that it's going to affect these two factors, right? So we can do it. And then what we are going to see is that, in fact, if you eliminate this, there's going to be a new connection that we should be adding like this, right? Why? Because now that this node is gone, we had two factors, so this new factor should be accounting for whatever observation was included here, right? So this is going to be the new equivalent factor, right, if we eliminate landmark 1. Yes? Which factors? This thing. Yeah, so this is what we are doing. Since we are removing these two observations, these two factors that were connecting this node from landmark 1 to x1 and x0 to m1, we can create an additional new observation. This is a virtual thing just to preserve things to have the same kind of distribution. We don't know exactly what it is, right? But we know that we can, from the graph perspective, we can, I mean, it's to be solved, right? But then the factor that we should be adding is something that compensates for these two observations. If you just remove this is not right, right? You need to add more information just to make the same, the two graphs, like equivalent, right? It's still to be seen what is exactly this new, but for now, let's not discuss. You will see in a moment, right? So then we have eliminated this, and what it means is that we are going to have new factor, new thing that looks like this. Well, here I'm just adding this, and this is landmark 2 now, and this is this and this. And then there's going to be a new, well, this new factor that I'm adding here, this one, right, that it's just going to be connecting x0 and x1. Right? Right, so this, yes. Why do we want to eliminate M1? You will see in a moment, but one of the motivations is maybe you want to reduce the number of variables that you want to estimate, right? It's actually a bad idea because in fact, what you are doing is, let's say, removing part of the structure of your problem. And then what this thing is, this is a little not clear, right? But in this case, the exercise starts with this. So we want to eliminate this landmark. And if we do, then these two observations are equivalent to this new observation. In this case, what we are connecting is state to state, right? Before, these two things are exactly the same. But for this, we have changed. Like two observations become now a new one observation. Okay, so we can keep going and doing this another time. In this now, we are going to eliminate M2. If we eliminate M2, we can have something like this. At this point, don't worry about what is exactly these new factors that we are creating, right? But, okay, so in this case, we have kind of the same thing. After eliminate. Okay, so you have another thing in your notes with more landmarks, but the idea is the same. And then the adjacency matrix that we obtain, it's going to be like this. This is odometry. Okay, I'm going to use a different color. And then here we have these two things, right? So this was after eliminating M1, and then here this is after eliminating M2. Here what we have is x0, x1, x2. There's no landmark. And now the big question is, what is these things? Right? They are connecting poses. What is exactly this thing? We are not observing anything. We don't have a function to describe this, right? So, but everyone agrees that if we eliminate, there's going to be like this new information that we need to add, right? So then what I'm going to discuss is like a connection with the Schur complement. And actually, you will see that eliminating these landmarks is equivalent to marginalizing these landmarks, right? So we have left, so we had so far like the discussion always between two fronts. We were talking about graphs, and then we talk about linear algebra. Now we have a third new way of explaining things, right? And it's the probabilistic perspective again, right? So it comes again. We started with this on this class. We left it a little behind to explain all this graph structure, but now it comes again, right? So if we explain this with respect to the Schur complement, which is a way of marginalizing variables, right, in our in our covariance, then things are going to be a little more clear. So relation, well, okay, so we have arrived here. If you calculate the information, it's still true, right? You are going to get an information form. It's simply going to be a little dense because here you have less landmarks, and then it's going to have less variables. But let's explain this from the Schur complement perspective, right? So we start with the full information matrix, the one that we had before, right? If you want, let's write it this way. So we start with this adjacency matrix multiplication, and then what we get here is that we have like information regarding these four terms, right? So it's information well, the information matrix for the landmarks, for the states, and then cross terms, right? So we can also divide this vector of update variables, right, into a part belonging to the trajectory and a part belonging to the landmarks, and then the same happens for this, right? So right, it's going to be a vector with respect to x and a vector with respect to landmarks. And what we did last lecture when I was talking about the Schur complement is saying that since this thing is diagonal, right, we can do a very efficient way of eliminating this block matrix from the full information matrix, right? And then at the end, what we get is some sort of, we have removed all the variables with respect to the landmarks, right? So this is another way of explaining what this landmark elimination is from our graph, right? If we come here, we say, okay, so we are just going to remove all these variables, and then the resultant information matrix, we know actually how to calculate it. Right? So if you remember, if you remember, it was the result. It was something like this. This was applying Schur complement. Remember, this is easy to invert. Right? So does this look familiar now? So what we have is an equivalent problem. Now we can say that this is the new covariance matrix, if you want, after removing landmarks, and actually this is equivalent to marginalize. So if marginalization was very easy in the covariance form, in the information form it's not that easy. But you remember that conditioning covariance actually resulted in the Schur complement, and the amazing thing is that there's a duality between covariances and information matrices, right? The duality is that what is easy to do for covariances, which is marginalizing, okay, so nice. What was easy to do for covariances, right? It was not that easy. I mean, it was just easy to marginalize, and this is taking the subblock, right? And then conditioning was, do you remember, it appeared the Schur complement. Okay, and now what we have here for information is that conditioning, we have seen that it's very easy, right? Remember, when we add a new information, there's almost nothing that we do. We just add new terms, and then things happen there easily, right? So adding new information, it's very easy. But now what we have seen is that, in fact, landmark elimination is a little more complicated. We cannot really marginalize an information form, but what we see is that here, as a result, what we get is the Schur complement. So this is the result of, let's say, marginalizing, removing all landmarks. And now all the three things together combine and explain like things rationally, right? So from the graph perspective, we are just eliminating landmarks. Good. So we come here, and then we say that after eliminating landmarks, this is our prime adjacency matrix, and things have just moved away. And then if you calculate your information, it's going to be whatever new thing, right? But we don't know what it is. But we know that actually this is equivalent if we add like the right factors. And now comes the Bayesian perspective, right? If we treat this not as a graph, but as a joint Gaussian distribution, that we are simply eliminating part of it, and in this case it's marginalizing an information form, then by applying the Schur complement, actually what we are doing is marginalizing, right? So all these, well, equivalent. It's not exactly, but all these variables just go away, and actually it's not that we know that there's going to be something, but we don't know what it is. We know exactly how this result is going to look like, right? And it's after calculating the Schur complement. So this new equivalent matrix is going to be an information matrix that only takes into account state variables, x state variables, but at the same time, it's also taking into account the previous landmarks, right, by removing them correctly. Right? It's not just saying, yeah, we don't care about this. Just solve this, right? We know that this is not correct. So it's correct this form, and actually, yes. Now everything is kind of explaining the same thing. So the Bayesian perspective from marginalization, node removing from graph theory, right? All these things at the end they are helping each other and complementing, right? So if you want to calculate what is the information form, if you want to remove all landmarks, because maybe you don't want to calculate them. This is what we said last day, right, about well, the Schur complement. Actually, what you are doing is just marginalizing them. Okay, think about it. Yeah, so marginalize landmarks and removing landmark nodes from your graph, all of them is equivalent thing. One is basically changing the adjacency matrix, but we don't know exactly in which way. The other is telling you exactly how the matrix, the information matrix should look like, right? And this is after considering whatever observations is there. No, that part I didn't explain. I'm just, what I explained is this in lecture 3. And this is not explained now. But if you want, you can go and redo all the completing the squares again for information form. And you will see that when you condition, things are very easy, right? It's almost trivial. But when you want to marginalize, you are going to have matrix after marginalization that it's going to be calculated by the Schur complement. So this is something that I'm not going to derive. You know how to do it. But this is an interesting result that, okay, if you go deeper, you can show it. But I think at this point you are convinced that for covariances that was true. So for information form, this is also true. There's some variants, right? So conditioning is not exactly as easy, right? You still need to do some things with the vector norm, or with the information vector, and well, but the intuition is that. So that's why eliminating landmarks, it was not that easy in graphs. That's why we get all these different results, right? Because actually what we need to do is a Schur complement. It's not taking blocks. It's a little more involved. Okay, and now this brings to the last topic of today, which is called post-SLAM. So if we get to this point, we have eliminated all landmarks. Then what we get here is just relations between state variables, nothing relating to landmarks, right? Landmarks are kind of a mean to connect different state variables, x state variables, but they are no longer used, right? And if we come here, then we see that these relations actually, what they are is just relations between poses, right? So with this, we can calculate correctly covariances, right, by the Schur complement. But post-SLAM, it starts from here, right? So what if you don't need landmarks at all? You don't want to estimate them. You just want to know where you are, right? Then what you need is a new kind of observations that, well, we had odometry previously. This is a kind of post relation. But we need a new kind of observations that relates different landmarks, right? So, well, in essence, post-SLAM is only considers poses. Okay, let's do the following example in 2D. Right, we start like here at x0. Well, I'm gonna write like a triangle, x1, x2, x3. Okay, so we are in this long journey. There's no landmarks, nothing to see. It's not boring, but still our system needs to estimate the state. And then we get to a point where we are visiting places that we have been before, right? So this is what we mean by observing other poses, right? So in this case, maybe there's a function. We need still to define what is this observation function. But maybe there's a way to add this observation. Right? And maybe from this pose also, we are also able to observe whatever was previously observed here in X1. Right? So that means that we are adding connections between these two poses. There's something on the environment. Now it's not landmarks. Before, the connection between poses was done through landmarks. Right? But you need to abstract away the fact that there's no landmarks now. So before it was this. Right? But this is the way of connecting different poses. Now we don't have that because whatever, we have marginalized them or whatever other problem you want to bring. And then simply means that there's going to be some relation between these different poses in time. Okay, and then maybe we keep going. And then there's a sixth variable, which is also observing, I don't know, this thing, right? So this is 3, 2, 1. What? This is the point, right? So far, what we know is that what we were observing is landmarks in common. This is very clear. Now, you can either assume that you have eliminated these landmarks, but this is still a way to connect poses. So maybe, although we don't consider this in the graph, there's landmarks connecting these two poses. Or there's another function, and in this case, this function can be point cloud alignment, right? So this is a new variety maybe that I'm adding here, but there's other observations functions based on sensors that can actually be relating different poses, right? So landmarks is clear. There's a feature in the space that you observe several times. Now, this can be redefined. It could be either observing the landmark, but simply not considering it into the graph, or it could be any other function, right? For now, let's say that this is the graph structure. Okay, and then, how are we on time? Oh, we are, okay. So factors, which are our observations, right? What we have is old odometry factor. This is almost always going to be with us. And then what we have is, by whatever observation function it is, we are going to have relative pose observations. This is also known as loop closure, right? No, we are not in the same point. If you see, these state variables are different. All I'm saying is that from one, you can observe another one. Let me give you a very example, right, that comes from computer vision. So we are here. What I'm seeing is that here, there's a class, right? And there's a guy talking here, okay? Kind of. And then there's another thing, right? So you observe this. Now you need to use a little your imagination. You observe this from this X1. Okay, so this is your camera and you are seeing this little guy here. Okay, so now we are in X2. And we observe something else, right, on the camera, but now instead of being exactly like this, it's the same, but with another thing, right? So there's part of the image that we have observed. this would be a way to say that we are observing the same pose, right? Just by using all visual features in an image. The same is true for LiDARs, right? So you could have a LiDAR observation and then saying that these two LiDAR observations have like in common like one rotation, right? And then basically what you need to find is what is the transformation that allows you to move from this pose to this new pose. Okay, so if you see here, we have shifted a little, right? But we are observing the same thing. Imagine here, maybe you have like a lot of different landmarks. So this is landmark 1, landmark 1, landmark 2, right? Or if you don't want to use landmarks, you can use just the full image, right? Or the full sensor information. That's still to be decided. This is a new modality. That's why we are introducing pose-SLAM as a new thing, right? Because now you need to forget about landmarks. You can get there by marginalizing all them. But at the end, what you are going to find is that there's a relation between these two poses, right? By whatever means. And usually this relation, what it is that there's a way to transform from one pose to the other, and that's what we are observing here, like relative poses. Okay, is this problem a little clear? What is exactly loop closure? How we can still solve this LAM problem without landmarks? Yes? So it's not the end of the world. Landmarks, let's say, it's like these little wheels that you have when you start going on your bicycle, right? It helps you to understand a little the problem. It's useful. I mean, landmarks are actually very useful, and they provide a very accurate description of your covariances, right? But this is not the only way. And if you don't want to calculate all landmark positions for some problems, well, maybe they are not necessary. So either you find another kind of observation functions, right, that are giving you, either you find a new observation function, which we have discussed this. This observation function, when you apply this to your problems, it's going to be whatever you want. It's going to be whatever you want. You just need, if it's nonlinear, to linearize and then apply all the algorithms that we have explained. But this, you need to think about it. What is exactly this observation function? What am I observing? And from this, we always build a probabilistic model. Now, it's a little change in paradigm, right? So in this case, I was explaining like visual loop closure. Right, so in this case, yes, we are adding this, but the same is true for LiDARs, any kind of sensor, right? That you have some way of measuring if you are observing a previous landmark. Okay, so by the way, so what is the price to pay? So for each of these poses, it comes associated an observation, right? So you cannot really remove it. In this case, if it's a camera pose, then you need to save this camera image, right? Because later, if not, how are you going to do like association? So it's going to be there. Imagine this as a feature or kind of a signature, right? The signature that we were using for beacon and range landmarks, right? So it could be like full image, right? Why not? And then it's not just about identifying landmarks, but it's about identifying previous poses. Okay, so I hope it's clear. No. Yes? It's just a little change in the paradigm, but no one at this point should be afraid of pose-SLAM, right? If something is not clear, we will go back, because all the definitions by now should be clear. But the important thing is that we just care now about trajectories. We forgot about landmarks by whatever means, because we marginalize or because there's a new function. But this state estimation is just about trajectories. Okay? The same variable. I haven't defined so far any variable. I'm just defining like factors. Yeah, well, this is for this particular example, right? It's to be seen exactly what it is. I'm going to define it now for the easiest example, that is two-dimensional pose-SLAM. But yes, there's going to be an observation function. There's always an observation function. Okay, so if we do it this way, then let's discuss like observations into the poses. So imagine we have something like this. We are in a global coordinate frame. Here we have the position of the I state variable. And then what we observe, similarly as we have proposed in this graph here, right? We are observing from one pose another pose. Okay, so I'm just like adding this part to the interesting part where we are observing a couple of poses, right? A pair of poses. So we have this. Now, the observation is going to be this. We can say that from pose 1, we are observing the second pose. And actually, we know that how can you observe a pose? So it must be another pose that is connecting this, right? So that means that this observation is also going to be x, y, theta parametrization. This is going to be more clear when we start talking about rigid body transformations, right? But for now, I think what you need to think is that there's a function that is giving you what is this relative pose, right? So from I, imagine that you can directly observe the robot. So if you had two robots, this will be very clear. So you will have like, I don't know, or someone. You will see this from your position, right? And then from this, you can basically, same as we did before, you can calculate your range, like your bearing, right? And then you calculate the distance. So this is the same analogy. Imagine that you are here observing a landmark, but now instead of being a landmark, this thing also has like orientation, right? So you also need to calculate what is the, yeah, I think this is the best way to explain this. You have a rigid body that you are observing from your position here, although this is virtual, right? But you are observing another rigid body, and then what you need to calculate is where it is. So in this case, in front of me. You are not rotated, well, yes, you are rotated like 100 degrees, and you are, I don't know, 5 meters, right? So this will be my observation. In global coordinates, this is going to be a different thing. But here, take a look, it's just in front of you, right? Then here you can calculate what is the distance, and then you can calculate what is the bearing. Very similar as how we were calculating landmarks before. Okay, you will see maybe a little more clear this when I write the function here. So we have this observation. Here what we are saying is that, remember, always from I, we observe J. So that's what I'm putting here. So what is the, if you want to calculate what is this observation here, what is this going to be? So we have here the position of J. We have the position of I, right? So it will be this vector. It's very similar to the way that we were defining landmarks, but there's going to be an extra thing you will see in a moment, right? So this vector, this is in global coordinates, right? So that's what I'm writing here, these global coordinates. So you have this thing that is in global coordinates, this which is in global coordinates, and this difference is in global coordinates. What do we want? We want this vector to be in local coordinates because we are observing from I, right? So that means that I is the local frame. Okay, so if we want to transform this to A, then basically what we need to do is rotate this vector, right? There's no need to translate it, it's already translated. Right, remember that this matrix of rotations was, for 2D, it was something like this. So this is the cosinus, sinus minus sinus cosinus. Again, these things appear a lot. Rotations in 2D. Orthonormal matrix as well, and a group of the SO2. Oh, wait. So we had a question there. Sorry. I move on because I wanted to finish this. Yes, so the question is, how is this different from the observation function for landmarks? Yes. It's going to be different now, because we also want to estimate this pose, right? But now let's think let's think a little on what we are giving here. It's actually almost the same. I would say it's the same, but the difference before is that our previous observation function had like range, bearing, and something else. And here what you are going to have is, okay, let me finish this, and I'm going to go with this. So lecture 5? I don't remember lectures now anymore. Okay, so what we have here, you will agree that here we have an x, well, a delta x, we have a delta y, and here what we have is a delta theta, right? So before what we had is you could have this x delta, this displacement in x and y as polar coordinates. So this is what we had before, this is overall. But now what we have is an extra displacement, because before we were observing a point, right? And now what we are observing is something with pose, right? So it's a way of thinking about it, but pose, it's going to be important. If you don't observe a pose, that means that your transformation is not complete. You don't know. Basically, you have a degree of freedom, right? You could be anywhere well. So to account for this, you have also this increment in theta. I'm going to explain later exactly how to calculate these things, actually in 2 lectures. But if you have heard about algorithms like point cloud alignment, ICP, RANSAC, all these things are kind of giving you these kind of observations, right? So you have like 2 poses, whatever observation it is here, and then at the end what you get is a transformation between the 2 poses. Okay, so this is it. This is our new observations of previous poses. Very, very, very similar to observing landmarks, but now with this extra thing on the pose, right? So there's also an orientation. And this changes a lot the structure of the problem, right? So in this case, we have here the adjacency matrix, and it's going to look like this, right? So we are going to have like all these odometry factors, I think 0, 1, 2, 3. How many do I have? 6, right? Right, so this is the new adjacency matrix. This is for odometry. This has not changed, but now we are going to have a new set of observations, which is different from before, right? We don't have landmarks anymore, and then, well, basically we need to determine this. So same as we did before, we need to add for all these loop closures. So if we had here like the odometry, just this long chain, this is clear, nothing changed, this is just the transition function, but now we have new 3 observations. So that means that from 5, we are observing 0. Remember, from 5, 5 is where we are. We are centered here. We should be seeing the relative pose to x0 in the frame number 5. So if we come here to the sketch of these variables, it should be something like this. From 5, we observe 0, right? And then there was 2 more factors that were from, do I need to go? From 5, we were also observing 1. And from 6, we were observing 1. Okay, so that means that 1 is going to be observed here by 5, and 1 is going to be observed by 6. Right? And this is our new loop closure observations that we are adding here. We are just connecting poses by saying that there's going to be a function, an observation function that relates them. Still, it's to be seen, but I can advance you now that for this, what you need is proper sensor information, not just landmarks. Landmarks are an abstraction after processing. You remember on this class on sensor, we discussed that landmarks are actually features or salient points in your scene, which has like a physical location. That abstraction worked well, but I think now we need to move on a little to talk about other approaches. And well, now it's the time, right? So there's going to be a function relating these two poses, right? In an essence, it's kind of observing the other another object. Yes, please. No, no, because 5 and 6, where do you see that they are the same? Yeah, okay, let's take this observation, right? It's relating 0. No, actually from 5 and 6, you only have one observation, and it's the odometry. Let's take the example. I think this is what you wanted to say. Is 0 equal to x6, right? Is x0 equal x to x5, right? So here what we are observing is 0 and 5. And the answer is no, because this set is not 0. It could be 0, right? If it's 0, then yes, they have the same value, but they could be different, right? So what you are saying is simply relatively from 5, where do you see 0? If they're exactly aligning the same thing, then you can say that they have the same value. But anyway, they are going to be different variables here. You cannot eliminate them. Because maybe on a next iteration, when you optimize, they are going to be slightly different. The poses of x0 and the poses of x5 in principle are different. If they were the same, then the observation that you should be seeing is 0. But it's not 0 in general. In general. So if the poses are the same, we come here to the equation. We have the same xj, xi. So you have here 0. And then the rotation is going to be whatever. It can be whatever number. It doesn't matter because you are rotating a 0 vector. And here poses, orientations, are the same, right? So you are just subtracting the same thing. So that's why you are going to have a 0 observation. But in general, this is not true. In fact, they usually correspond to different poses over time. So you cannot say that they are the same. You should be treating them differently, although they have the same value. Because maybe later the optimization tells you, look, you know, you were not exactly there. You were exactly a little shifted, right? So still you are close by. The observation is kind of matching, right? Imagine this is I mean, we always have an observation model, and it should be fitting whatever we observe, right? So it might be close, it might be not so close, but it should always be likely, right? Close to whatever mode we have. So this is a very important distinction. I think everyone, well, we have another question. This is another way of looking at it, right? So you could have like this kind of system of one odometry and then another odometry. Effectively, it's the same thing, right? So here you have like these frequent observations, right? You are adding all of them just to subsequent poses, and here you have whatever other system, maybe visual odometry or another way, that actually what is giving you is the transformation, but not with respect to subsequent, but different ones. So in this case, yes, this is another way of pose SLAM, right? Here, maybe to calculate this, there's going to be landmarks, but you don't care about them. Landmarks are just a way to connect poses, right? This is a good comment. I think, well, take a look at this. It's simply a little change in paradigm, but most of the things that we have said apply. The algorithm is exactly the same. It only changes how we are now calculating Jacobians and all these things. But, well, it's just food for thought. You can think about it a little later, maybe after the exam. Okay, and if we were discussing about how to fill this adjacency matrix, then there's a very important detail, which is the Jacobians, right? So in this case, we have the K observation, and we want to relate it to whatever pose we're observing, right? So this basically comes here. And we need to derive with respect to xj and theta j, right? So this derivation is easy. What it's going to be here is this rotation, because this is not dependent. I mean, this rotation depends on I, and we are deriving with respect to j. And then the Jacobian, it's going to be similar here. It's simply the same, but negative, right? Here we still have zeros. And then here, this comes a little non-conventional thing, and it's because of this. So we need to derive with respect to theta, and rotation depends on theta, right? So we need to do the derivative of this, right? So you keep this as delta of whatever, and then we take here this matrix, and then if we derive all cosinus and sinus here, well, what we get is this minus sinus delta x minus cosinus delta x minus sinus. Okay, you don't have to implement this, but you have this on the notes. And basically, that's totally determined now. The only big question is how to obtain, right? Which is something that you ask in case that you are not considering landmarks to be removed. So how can we obtain this? And the answer for this will come in a couple of lectures, right? So we are going to explain like alternative observation functions, not with landmarks, but in this case, well, the problem is commonly used. So it's registration, right? You have a couple of images, a couple of sensor readings, and you want to align them, right? So you need to find what is the transformation that allows you to match whatever you're observing from one sensor and whatever you're observing from the second sensor. There's going to be a transformation. And here I'm saying this, it's a rigid body transformation between the two observations, right? If you find this, which is usually found by optimization or direct algorithms, then you have the observation that we need, right? But for now, what you need to know is that, well, whatever we find, it's going to be affecting the graph structure this way, right? So we are going to have a lot of factors that now are going to be connecting poses, right? No landmarks. Still, we can solve the problem. Okay, so that's it for today. Now, I'll see you, all of you, tomorrow in the exam. You can bring your piece of paper with written things. You have like some samples in Canvas, but the exam should be easy, right? If we have followed all the problem assignments and classes. And I wish you luck and strength. See you tomorrow.